Hello everyone. This is the CO2-O2 calculations part 2 lecture. We've looked at the carbon dioxide formulas, which we mainly used for calculation of physiologic dead space. This will focus on oxygen formulas. And as we see, there's a lot of information. So I've divided this in between a couple of different illustrations here. And you'll see some of this in your book as well. But I'm going to start out here in the external environment, the atmosphere. Look at Dalton's law. Dalton says that if we add all of the partial pressures of gases and water vapor together, that we will get the total, which is the barometric pressure that's in the atmosphere. So again, adding all partial pressure of gases in the atmosphere together gives you the total, which is the barometric pressure. What I did was take barometric pressure of 760 torr, which we know is barometric pressure at sea level. I multiplied it by 21% fraction of inspired oxygen to get a PO2 of 159 torr. So again, 760 times 21% gives us 159 torr, which is the PO2 in dry air at sea level. Inspiring 159 torr for our PO2, we see that by the time it makes its way down into the alveolus, it's only 100 torr approximately. That's our P big AO2. So to solve for alveolar oxygen, again we've got that alveolar air equation, which you'll recognize, barometric pressure minus water vapor pressure, multiplied by the FiO2, and then from that we subtract the patient's P little a CO2 divided by the respiratory quotient or respiratory exchange ratio, which is 0.8. Plugged in all of our values, okay, and we see that the result is approximately 100 torr for a P big AO2, and that's under normal circumstances, normal conditions. So I simply solved the alveolar air equation, giving us 100 torr, and I put that here in our alveolus, 100 torr. Gases exchange until they equilibrate. So here in the pulmonary capillary, I've got the partial pressure of capillary O2. Little c with a hyphen is capillary, and that's always here at the pulmonary capillary. So if our alveolus oxygen level is 100 torr and gas exchange occurs until equilibrium, then the oxygen partial pressure in the pulmonary capillary should achieve 100 torr as well. Also, the gas will be completely saturated in blood on that hemoglobin, so we'll have the saturation of pulmonary capillary oxygen being 100%. All right. As we move into the left side of the loop, we have a little bit of venous reduced hemoglobin added, which reduces the partial pressure of oxygen in arterial blood, and it also reduces the saturation a little bit. So we know the PaO2 is 80 to 100. I just created the 90 torr here just as an example, and saturation is usually around 95-97%, so I used 95. This is actually what perfuses the tissue bed where gas exchange takes place again. And then the venous gas moves back to the right heart from the inferior and superior vena cava, which gives us a mixed venous gas here in the pulmonary artery. We always release approximately 25%, about 1/4 of the oxygen to the tissues, which is a value that you can remember to help you understand that the venous oxygen saturation is 75%. So if it hits the tissues at about 100% and gives up 1/4 of the oxygen, then the returning oxygen level is about 75% or 3/4. The resulting PVO2 is 40 torr. And we're going to see this again a little bit later, but the saturation of gases occur on the hemoglobin unit. The partial pressure of a gas exists within either another gas or within a liquid. So the liquid constituent of the blood, of course, is the plasma. All right. This next drawing ties in some more connections for us. This at the very top illustrates what I just said earlier, that the oxygen that's in the blood is divided between the hemoglobin and the plasma. If we refer to oxygen saturation, we're looking at the oxygen that has saturated the hemoglobin unit. If we're talking about partial pressure of oxygen, then it's residing within the liquid portion of the blood, which is the plasma. Interestingly, if we only talk about the saturation or only talk about the partial pressure, we're not talking about the total. To determine the total oxygen, we actually have to add both of these components together. And when we do, we can start referring to the total oxygen that is in that part of the blood, which is referred to as capital C, or content. So oxygen content is derived by taking the saturation on the hemoglobin as well as the partial pressure in the plasma. Okay. This is a lot of information, so I'm actually going to stop the lesson here and then pick up with part 3.